Okay, so welcome to this content chemistry class. So just like the other classes, we'll be going over quite a lot of content. And if you've got any questions as we're going along, just drop them in the chat and I can see them on screen. So let's jump right into it. So we'll start off with the basics of chemistry and essentially what everything is built upon in chemistry, and that's atoms. So an atom is essentially the smallest building block of anything that's matter. So when we say matter, we mean something solid, liquid, or gas. And they're made up of 3 subatomic particles. So we've got the nucleus, which is different to the nucleus that's in an animal and plant cell. So don't get confused with that. A nucleus just is the definition of the center of the nucleus. And in there, we've got protons and we've got neutrons. I'll just call them differently. We've got protons and neutrons at the center of the atom. And then we've got shells around the atom. Now, a shell is essentially where the electron lives. So I'll just say there's an electron there. So what you need to remember is the nucleus is still on an atom and the electrons orbit that nucleus. They're the ones that are moving. So out of all these subatomic particles, I would say the electrons are probably the most important. That's one you will keep hearing about throughout today and throughout GCSE as well. So we've got the electrons in the shell, and then in the nucleus, we've got the protons and neutrons. Now, for each of these subatomic particles, you need to know what the mass and relative charge of them are. And this is important when we're looking at the periodic table and we're figuring out how much protons, neutrons, and electrons certain elements have. So let's make a little table. We've got proton, neutron, and electron. So I wouldn't say just memorize these, actually understand, well, why is it like that? Okay, so the relative charge and the relative mass. So in terms of the relative charge, the protons are positive, so you can remember that by pp. It starts with a p, so it's just positive. The neutron is neutral, which means it's got no charge, and the electron has a negative charge. So overall, the nucleus, if you think about it, you've got positive, we'll say these are the protons. They're positive in the middle and neutrons. So overall, your nucleus is positive, and your electrons are orbiting around are negative. So there's attraction there. If you think back to physics, positive and negative attract. Okay, in terms of mass, how much do they all weigh? So this is just the relative mass. So the relative mass of both the proton and neutron, we just say it's 1. We can't have a negative mass. It's quite a common mistake that students will mix up their charges and masses and they'll end up writing a negative here, for example. You can't have a negative mass. It's impossible for something to weigh negative. And then for the electron, again, a lot of people put 0. I wouldn't recommend putting 0 because you can't have anything that has like no mass. There has to be something there. So a few things you could write here. You could say really small. You could say 1/2000. You could say 0.0005. So anything along them lines. But I'd recommend steering away from that 0. I know some teachers do just put a 0 there, but you can't really have a 0 mass. Okay, so that's the charges and masses of each of them. So how's that relevant? Well, if you get the periodic table, let me just copy this. And we have a look at the periodic table. Now, the periodic table is essentially all the elements that we know exist, and it just fits quite nicely in terms of its mass number, proton number, and so on. So if we have a look at this, let's get an example. Let's say let's look at sodium. So sodium represented by Na. Remember, when you're writing elements down, I can't write N capital A. It has to be N small a. Because if I wrote Na just like this, that's nitrogen and that's argon. That's 2 completely different things. So you have to keep it case sensitive. So sodium, how many protons, neutrons, and electrons does it have? To work out the number of protons, it's the proton number or atomic number. And we can see from this key here, actually, so looking here, it tells you that bottom number on the periodic table is the atomic proton number. So the number of protons in the sodium is 11. Now the number of electrons from the periodic table is exactly the same. So that's also 11 as well. Now, the reason why this is, they might ask you, well, why is the number of protons and electrons the same? The charges of everything on the periodic table is neutral. There's no ions. So ions means it's got a charge. Elements are all neutral. So therefore, if protons are positive and electrons are negative, they have to have the same number to be able to cancel each other out. So that's the reason why the protons and electron number is exactly the same. And for the neutron number, to work that out, you just do the top number, which is the mass number, which it also says on the top here, it says relative atomic mass, and you minus it from the bottom. So we're doing 23 minus 11, which just gives you 12. So the number of neutrons is 12. So again, they might ask you in the exam, what's the reason you can just minus the top and bottom number and it gives you the neutron number? Well, this top number, the relative atomic mass, is just the number of protons and neutrons. The number of electrons is not included in the overall mass because it's really small. So you can see how you can use this table here to explain your reasonings as to why we do certain things on the periodic table. Okay, so that's a little bit about the atom as we know it today. So that's the atomic model today. You need to know about the history of the atom, how they ended up like coming to this point, and you need to know the name of a few scientists that actually got us to this point as well. So before anything, before like I would say this was before Thomson, they thought the atoms were just tiny spheres, so they didn't know about subatomic particles at that point. So history of the atom. So at first they thought they were tiny spheres. This is before the discovery of the subatomic particles, as I just said. And then after, Thomson came along and he came up with the plum pudding model. Now, what the plum pudding model is, if I can just get a picture actually rather than drawing it. Plum pudding model. So as you can see, I'll just put that on here. This is not how we accept it today. Copy image. Okay, so that's what Thomson believed. He believed it was a ball of positive charge with these negative electrons dotted all around it. So at this point, they still didn't even know about the neutron. It was just the proton and the electrons they knew about. So it looks a bit like a plum pudding. It's just all spotted everywhere. So that's what he thought, a ball of positive charge. That's why there's that big positive there with negative electrons just scattered around it. Rutherford then came along. So the other scientist, Rutherford, he came along and he said that the plum pudding model is wrong. And the way he proved that it's wrong is he did the alpha particle scattering experiment. Alpha particle. And essentially what that was he got alpha particles and he fired them at a gold foil, and some essentially deflected back, so showing that the plum pudding model was wrong. So so the results led to the conclusion that the mass of an atom was concentrated at the center, which then kind of was coming towards what we've got the nuclear model today. He essentially said that there has to be some sort of nucleus. At this point, he still didn't know about neutrons. He thought it was just the protons in the center. And then finally, we've got Bohr. Bohr's got Chadwick as well, actually. So you need to remember the scientists and names as well, not just what they did. So Bohr came along. He adapted the nuclear model by suggesting that electrons orbit the atom, the nucleus, sorry, but at different shells. So Rutherford just says they're around it, but Bohr actually came up with the shell theory. So there's multiple shells, which we'll come on to as well. So he came up with the shells, so electrons orbiting. And then finally, the only thing that's missing, I guess, is the orbiting, is the neutrons, and that's where Chadwick comes along. So he determined that the nucleus also contains neutrons as well. And then that's the nuclear model that we've got today. So remember each of the scientists' name and how they contributed. essentially. Okay. How do we do electronic structure as well? So in terms of electronic structure, it's just the number of electrons an atom has. So if let me move this down. So if we look at sodium again, so when you're told the electronic structure, that essentially just means draw out its electron structure. And the rule that you need to know in GCSE is not entirely right, but it's just something that you need to know for GCSE. The order they'll fill in is 2, 8, 8. And they will never tell you more than 3 shells to draw. You go to a 4th shell. It's usually at max 3 shells that you need to draw. So if you have a look at sodium, we said sodium has 11 electrons. So looking at the electronic structure rule, 288, put sodium in the middle. 2 electrons in the first shell, so 1 here, 1 here. Now, try and not draw your electrons like this, close together. Try and draw them as far apart from each other as possible. And the reason why is electrons are negative. So if I've got 2 negatives together, that repels. Same charges repel, opposite charges attract. That's the reason why we draw them as far away from each other as possible. So we've drawn 2. We still need 9 more. So we can't draw 9 in the second shell. We can draw 8. So let's draw 8 as far as possible. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so far we've drawn 10, but we need 11. So we need 1 more shell. And then that's where this goes here. We'll do 1 more. Let's do carbon. So carbon has 6 electrons. Has 6 electrons. Again, going by the 288 rule, I can put 2 in the first shell. So I've got 4 more to draw. So in the second shell, I can have a maximum of 8, and I can just put 4 there. 1, 2, 3, 4. Okay, so that's about electronic structure. Now let's speak a little bit about the periodic table. And understanding what the periodic table is essentially telling us. Okay, so first things first, how is it arranged? So this is the Mendeleev, he's kind of come up with arranging it in this order. Otherwise, before they kind of just listed them all out, he left gaps for undiscovered elements to essentially be slotted in. And just realized as well, so the last few rows of the periodic table is missing for GCSE just because it's a bit complicated. You don't really need to know about them. Okay, so the periodic table. There's 2 kinds of elements that you can have. There's metals and there's non-metals. So don't say metals and gases because them non-metals aren't just gases. They could also be liquids as well. And how do we determine that split? Start off with aluminium here. This is where the step starts. I'm just going to draw the step here. So the way I remember it is aluminium is a metal. You find it in your kitchen as kitchen foil. So that's where your step starts, and then just draw the step down. Now, everything to the left of that step is a metal. Okay, can you hear me now? Okay, awesome. Anyways, as I was saying, so the next thing we've got is group numbers. So the group numbers essentially tells you the outer number of electrons. So we looked at sodium up here. Sodium's got 1 outer electron, so it means how many electrons are in the furthest shell. So we've got 1 there. So that should be in group 1. which is sodium is in group 1, which you can see here. Carbon has 4 outer electrons, meaning it's got 4 in its outermost shell, 1, 2, 3, 4, and therefore it should be in group 4. And if you have a look, it is in group 4. So why is this important? Usually when we're looking at bonding, we don't really care about any of the inner electrons when we're joining atoms and elements together. So that's the reason why we have a group number. Take, for example, cesium. If you're bonding cesium to something and it's got 55 electrons, you don't want to draw 55 electrons. You just want to represent cesium. It's in group 1. So therefore, it's just got 1 outer electron. And that's how we represent it in bonding. We don't actually draw everything of the atom unless they tell you to draw the full structure of the atom. Okay, so keep that in mind. That's where group numbers are important. So group number is outermost electrons, meaning the electrons in the last shell. Okay, but we've got group 0, so surely that doesn't mean 0 electrons in the outer shell. What group 0 is essentially a full outer shell. So we call these the noble gases. In some periodic tables, you might see that as group 8. So this is the AQA version of the periodic table. Have a look for your exam board what they've represented it on there as, but most likely it is group 0 rather than group 8. The reason why is, let's draw helium. Helium's got 2 electrons. So that's a full outer shell. It builds up the full first shell because 2 is the maximum that can go in the first shell. Okay, so that's a full outer shell. Let's look at neon. Neon's got 10 electrons, meaning it's got 2 in its first shell, and then it's got 8. So 1, 2, 3, 4, 5, 6, 7, 8. So full outer shell, and it's got 8 in its full outer shell. So as you can see, there's 2 in the outer shell here, and there's 8 in the outer shell for this one. So that's the reason why it's just represented as group 0. So noble gases have a full outer shell. They don't really react with anything for that reason. We call them inert. So the word inert means not reactive, and it's got no reason to react because it's already got a full outer shell. The whole point these elements react with each other is because they want to get stability. They want that full outer shell, which we will come to look on when we do bonding as well. Okay, in some periodic table, you get the period numbers, which is the rows. It's not here, but what the rows essentially tell you is how many shells they've got. So for example, so this is the first period, which you can see we've only got helium and hydrogen. The second period, the third period. So if we look at sodium, it's in the third period. I can see it's got 3 outer shells. 1, 2, 3. So the period number just represents how many shells it's got. As you can see, as you go down, the more shells an atom's going to have because the bigger it is. So call them the period numbers, and that is number of shells. Okay. Okay, what else about this? Okay, hydrogen's free floating in the middle. That's quite a common exam question as well. Why is hydrogen free floating in the middle? Why doesn't it belong anywhere? Well, what is hydrogen? Hydrogen is, I'll do this in red. Hydrogen is a non-metal. So therefore, it should be on the right-hand side after that step. But if we draw the electronic structure of hydrogen, it's got 1 outer electron. It's just got 1 electron. So therefore, it should be above group 1. So sometimes you might see hydrogen here in some periodic tables. So because there's that confusion with it being a non-metal and with it also having 1 outer electron, they just keep it in the middle. So it's kind of the one that doesn't fit the trend, essentially. With hydrogen, a few properties that you need to know about it is it's extremely flammable, meaning it can easily ignite. So we'll come on to some equations that involve hydrogen and such as well. Okay, and then I'd say another thing to mention as well, these are the alkali metals, group 1, which we'll come on to looking at some of their reactions as well. And we've also got the halogens, which are group 7 as well. So you need to know about these as well and trends. So we will look at these into more details when looking at their bonding. Okay, so bonding. There's 3 types of bonding. I'm going to do this on a new page, actually. 3 types of bonding that you need to know about. They can ask you in the exam, they could show you any molecule compound and they'll say what bonding is present. So you need to be able to identify that. So the 3 types of bonding, there is ionic bonding, covalent bonding, and finally metallic bonding. Now to identify which one it is, it depends on whether they're metal or non-metal. So I'm guessing you already should realize with metallic bonding, it's a metal and a metal. Okay, what other options have we got? We've got metal and non-metal. So which one would that be? That's ionic bonding. So if we've got a metal and a non-metal bonding with each other, that's going to be ionic bonding. So the only one that's left is non-metal, non-metal, and that's covalent bonding. Okay, so that's how you identify which bonding is present. So if you have a look at a few molecules and compounds, let's identify them. So for example, CO2, that's an example of covalent bonding because carbon is a non-metal and oxygen's a non-metal. Ionic bonding, we could say sodium chloride. Sodium's in group 1, so it's a metal. Chlorine is in group 7, so it is a non-metal. Metal and non-metal, that's ionic bonding. If we've got something like just zinc by itself, well, zinc's a metal. If you have a look, it is right here on the metal side. So that's bonded with metallic bonding. Another example could be oxygen. That's covalent. We've got silicon dioxide. So silicon is, let's have a look. Silicon is a non-metal, so it's there. And then oxygen is there, so 2 non-metals, that's also covalent bonding as well. So yeah, that's a few examples on how you can identify it. So silicon dioxide, I've seen that as a common mistake. Students say that's ionic bonding because it assumes silicon's metal, but it's not, it's a non-metal. You can confirm that on the periodic table. Okay, so how do each of these bondings differ with each other? The way they differ is in terms of their electrons, what's happening with their electrons. So just like we spoke about right in the beginning, the electrons are the most important subatomic particle, probably out of the 3. So what happens? Well, with metallic bonding, the electrons just become delocalized. So delocalized electrons. Now the word delocalized essentially just means that they're free. But try and not use the word free, use the word delocalized instead. So if you think about metals, metals are very good conductors of heat. Conductors of heat and electricity. And the reason why they are is because of these delocalized electrons. Delocalized electrons allow a substance to become a good conductor of heat and electricity. That's why we use metals for heating. When you're able to heat it, it absorbs heat quite easily. It gets hot very quick. So if you're cooking, for example, you're not going to cook with a plastic pot. You're going to use a metal pot because it conducts heat a lot easier. And in terms of electricity, again, you're not going to use something that's plastic or wood, for example, to conduct electricity. There's a metal wire inside the plastic tubing to be able to conduct electricity. So that's the reason why metals are good conductors, delocalized electrons. Okay, what about the other 2? Well, with covalent bonding, they share electrons. And you'll see this in the diagram when we do an example. And then ionic bonding is a transfer of electrons. So they differ in terms of what they do with their electrons, each of them. Okay, so let's have a look at an example of each of them, and you could just see it in action essentially. So once you understand one example, you can apply this example to any example that they give you within the exam. So we'll take sodium chloride, that's a very common example with ionic bonding. Now, sodium is in group 1, so it's just got 1 outer electron. I'm not going to draw the whole structure of sodium like I've done up here because the inner ones have no relevance to the bonding. So I've seen that in exams where students draw the full structure. You don't need to do that, just the last outer shell. Okay, so sodium, just going to create some space here. Sodium has 1 outer electron. Okay, and I want to represent that with the cross. Chlorine is in group 7, so it's got 7 outer electrons. I want to represent this with a different shape. I'll use dots. 1, 2, 3, 4, 5, 6, 7. Okay, so remember with bonding, we essentially want a full outer shell. That's the whole point. So in terms of ionic bonding, transfer of electrons, one's going to lose electrons and one's going to gain electrons. Now the metals always lose electrons. So metals, they lose electrons. And don't just memorize it, understand why is that the case. Metals always lose electrons. You can see with this sodium here, if it loses that one electron, if we go back to this diagram up here, if it loses this one here, then losing that one means it's got a full outer shell underneath. So that's perfect. Now, why would sodium choose to gain 7 electrons rather than just losing one? It's less energy to lose 1 electron than gain 7. So that's the reason why sodium is going to lose that 1 electron, which needs to go somewhere. Now, chlorine, either it will gain 1 or it's going to lose 7. Again, why would it lose 7? That's a lot more energy to lose 7 electrons than just to gain 1. So in that case, non-metals gain electrons. So they gain the electrons. So, and it makes sense. So this sodium here is going to lose it and give it to this chlorine. Now with ionic bonding, ions are formed. It's kind of in the name. And what is the definition of an ion? I'll just put it up here. An ion is a charged particle. And what the charges you can have positive or negative. Now the question is, how do we know which one's positive? How do we know which one's negative? That is depending on whether it's a metal or non-metal. Now, if something loses electrons, they've lost something that's a negative. The electron was its negative part, right? So it becomes positive. So it becomes a positive ion. Non-metals have gained electrons, and remember the charge of electrons is negative. So if you're gaining something more negative, then you've become more negative. So that's a negative ion. And the charge number that it will be, it depends on how many electrons it gains or loses. So for the sodium, okay, can you hear me now? Not sure why that's happening. It's quite weird. Okay, so the metals lose electrons, so therefore they become positive. Non-metals gain electrons, so they become negative. Okay, so, and depending on the number that it's got, it depends on what you put in front as well. Okay, so that's an example of sodium chloride. The more common one that they ask you in the exam is ionic bonding to draw, because covalent bonding is quite difficult. But let's go over a covalent bonding example, and I'll do it down. Let's box this off. We'll do oxygen. That's quite a straightforward one that usually they ask about. So oxygen. Oxygen, what I would say is when you're drawing the covalent bonded structures is draw how many outer electrons they've got first. So what group is oxygen in? Oxygen is in group 6. So it's got 6 outer electrons. So let's just draw that here. Oxygen has 1, 2, 3, 4, 5, 6. So it's got 6 outer electrons. So how many does it need to become stable? It needs 2 more to become stable. So it needs 2 more to become stable. So if we know oxygen's diatomic, so let's say we've got another one, 1, 2, 3, 4, 5, 6. So each of them need 2 essentially to be stable. So because we can't just transfer in this, it's not ionic bonding, they need to share, so there's going to be an overlap. So that means this one needs to share 2 with that one, and the one on the right needs to share 2 with the one on the left. So that's where the overlap's going to come. So let's draw both our oxygens. So it's like you need to make your decisions beforehand. Here's my 2 oxygens. The reason why we call it diatomic, di means 2, so it has to exist with 2 of them. So the one on the right, the one on the left, sorry, needs to share 2 with the one on the right. So I'm going to put 2 crosses in the middle. Some people also draw on the edge as well. You can do that as well. I'm just going to put them in the middle, so they're shared with both of them. So the one on the left is sharing 2 with the one on the right. However, the one on the right also needs to share 2 with the one on the left, so that gets full as well. So 1, 2, so 2 pairs of electrons. So 1 here, and then there's another pair there. Now just fill in all the remaining ones. Now I've drawn 2 X's, but I need 1, 2, 3, 4, 5, 6 X's altogether. So I need 4 more. So 1, 2, 3, 4. Same with the dots. I've drawn 2 in the middle. I need 4 more. So 1, 2, 3, 4. And then just double check, each shell, have they both got 8? So if I look at this one here, the one on the left, 1, 2, 3, 4, 5, 6, 7, 8. So that one's happy. And the one on the right, 1, 2, 3, 4, 5, 6, 7, 8. So they're both happy. So as you can see, you're just sharing electrons with each of them. Okay, so that's how you represent covalent bonding. Usually they will help you with that, but it is quite tricky to do that, knowing how much needs to be shared with each of them. I'd say ionic bonding is the more easier one to draw. Let's have a look at metallic bonding now. How can we draw something that's metallically bonded? Now, this one's quite straightforward. Metals are positive ions, as we've already spoken about. Metals become positive ions. So you represent the metals. Where can I do it? I'll just do it here. 2, 3, 4. There's not a certain amount of like circles that you need to draw. You just need to represent some positive metal ions. So let's say this is zinc, for example. We're just representing a few positive metal ions. Now we've just said metals have delocalized electrons, and to represent them delocalized electrons, which are negative, you just put them in between. Doesn't matter how many you draw, but we call this a regular lattice structure that it just displays. Okay, so that's the top basic layer of ionic, covalent, and metallic bonding, but it does go further, like into simple molecules, the giant ones, and so on. So let's have a look at some of them examples. We can start off with, we'll start off with ionic bonding, we'll go in order. So with ionic bonding, there's a few facts that you need to know for each of these. But actually before, we'll go into ionic bonding first. Let's speak a little bit about ionic bonding and the molecules that they form. So ionic bonding forms essentially ionic compounds. And these ionic compounds have a giant ionic lattice structure. The giant ionic lattice structure. So a bit like the metallic one that I draw above, but let me get a picture to show you. There you go. So that's a lattice structure, essentially. So like in a 3D way of sodium chloride. So copy. Okay, so that's like a giant ionic lattice structure. So when it's solid, it does not conduct electricity, or does not conduct electricity because the electrons are not free to move, they're not delocalized. However, if you make this ionic compound molten, meaning you've melted it, then you can allow it to conduct electricity because the ions are free to move. So when it's solid, the ions are fixed in place, as you can see, when it's solid, but when you make it molten, the ions are free to move, so therefore it can conduct electricity. So you might get an exam question saying, what are the conditions for something that's ionic to be able to conduct electricity? You have to make it molten. It cannot do it when it's solid because the ions are not free to move. We can say that these ionic compounds also have very high melting and boiling points. And another way they can also conduct electricity is if they're in solution as well. So molten or in solution, because then the ions are free to move. So that's the reason. So the reason why it can conduct electricity is ions are free to move. Okay. Okay, and then one really important fact here to know about is they might ask, well, what's the reason that ionic compounds have very high melting and boiling points? And the reason that you give, and I'm going to put this in red, because the reason you give depending on which bonding it is different. For the case of ionic bonding, it's strong electrostatic forces. Now, whenever you see the word electrostatic, and you will end up seeing it in physics as well, electrostatic just basically means between positive and negative. So whenever you've got an attraction between something positive and negative, that's an electrostatic force. And in this case, we've got a positive sodium and we've got a negative chlorine. So that's the reason why it's electrostatic forces. Now, if we move over to covalent bonding now, we cannot use the reason electrostatic forces because there's no ions involved with covalent bonding at all. You can see there's no charges at all when you've got nonmetals involved with each other. So let's have a look at covalent bonding now. Write capitals just to keep it uniform. Okay, covalent bonding. So here, the reason that we're going to give, so I'll give you the reason first and then I'll explain the reasoning. So the reason why some simple covalent molecules, now when I say simple covalent molecules, I mean stuff like oxygen, water, carbon dioxide, so just simple molecules. The reason why they're quite weak is because they've got weak intermolecular forces, which you sometimes might see as IMF, so intermolecular forces. You cannot use that reason with metallic bonding or ionic bonding. Intermolecular forces is unique just to covalent bonding. So try and not mix these reasonings up with each other. Now, I just want to explain what intermolecular forces are because a lot of students confuse it for a covalent bond. A covalent bond is strong, but the intermolecular force is weak. So what's the difference? Well, let's say we've got a glass of water, and water is made up of H2O. So it's a covalent substance because hydrogen is a nonmetal, oxygen is a nonmetal, and it's a weak substance. Not weak. It's got weak intermolecular forces, but where? So in a glass of water, you don't just have just the one water molecule. You've got loads of them. So let's draw a few of them. So let's say we've got H2O here. Obviously, we're going to have a lot more than this, but I can't draw smaller than this. And I'll just write on the side that it's a glass of water so you remember the analogy. Now, that glass of water, between the oxygens and hydrogens, that is a covalent bond. So this here is a covalent bond. And a covalent bond is very strong. These are strong. So it's not the covalent bond that's strong, it's the intermolecular forces. But where are the intermolecular forces? The intermolecular forces are what's joining each of these molecules together. I'll just draw them in, get a different color. And we'll just draw them in this. The intermolecular forces are what join each of these together. So these here are the weak intermolecular forces. So whenever we're boiling water, we're breaking the intermolecular forces down, but not the covalent bond. So just to explain it to you, let's say we've got liquid water, which is in that glass. If we then freeze it, we get ice, but ice is still water. It's still H2O. Liquid water is H2O. Ice is also still H2O. So what have you overcome? You've overcome them intermolecular forces. That liquid water, if you heat it, you then change it into steam, so water vapor. But that water vapor is still H2O. You've not changed the covalent bond. You've just broken these weak intermolecular forces. So that's quite a weird concept that students can't grasp. So strong covalent bonds which do not change when you're moving physically between substances. So we call these physical changes. The reason why we call it a physical change is because the chemical's not changed. It's still H2O, whether it's ice, whether it's liquid water, whether it's water vapor. It's just the weak intermolecular forces that have overcome with simple molecules. So I would say keep this example in your mind with water because you can apply it to carbon dioxide, you can apply it to oxygen, this same analogy of weak intermolecular forces between particles. Okay, so I guess one that we've got left as well is what's the reason that you would give for metallic bonding in that case? I'm going to write this up here with metallic bonding rather than writing it again. But with metallic bonding, we've got a positive ion and we've got negative electrons. So remember when I said you've got something positive and you've got something negative, that's electrostatic. So the reason why metals are quite strong is the strong electrostatic forces. So it's the same reason, but it's just between different things. So in ionic bonding, the strong electrostatic forces are between the positive ion, so the metal, and the negative ion. But in metallic bonding, the strong electrostatic forces is between the positive metal ion, but this time there's no negative ion, there's a negative electron. Remember these delocalized electrons that they've got? That's what it's between. So the positive metal ion and delocalized electrons. I'll just write electrons. So same reason, but between different things. I'll keep that there. So there's a few other things you need to know about covalent bonding. So we spoke about some simple molecules. So simple molecules such as water, such as carbon dioxide, oxygen, chlorine, and so on. And now you also know the reason why they're diatomic. They exist diatomically, so meaning they've got two, because if there was just one, it's not a full outer shell, so therefore it's not stable. That's the reason why they bond with two. So they're simple molecules, and they're represented as we've just represented above, like with this glass of water. Now, we've also got giant covalent structures. Sometimes they're called macromolecules, but we'll call them giant covalent structures here. And for GCSE, there's a few that you need to know about. We need to, first of all, know about the allotropes of carbon. Now, what allotropes mean is substances which are made up of the same thing, so in this case, carbon, but because they're bonded differently, they give rise to different substances. So I'll tell you the examples. We've got diamond, we've got graphite, graphene. So all of these are made up of the same thing, but because that same thing, carbon, is bonded differently, they look different. So diamond, let's start off with that first. So they're all made up of carbon. What group is carbon in? So notice how I'm always going back to the periodic table as well to help me. You get this periodic table given to you in the exam. You should have a lot of annotations on it during as well. Carbon's in group 4. So it's got 4 outer electrons, meaning it can have 4 bonds. Okay, so this is also going to help you when you learn about hydrocarbons, alkanes, and alkenes. Carbon comes up quite a lot there as well. So carbon can have 4 bonds. You'll hear this quite a lot throughout chemistry because you deal with carbon quite a bit. Okay, so The way diamond is bonded, each of its carbons is bonded to 4 other carbons. Okay, so each carbon is bonded to 4 other carbons, and that structure repeats. So there's no delocalized electrons, meaning no free electrons. So I'll just get a picture. Okay, so there you go. That's what you will see it as. Obviously, we can't keep drawing that repeated structure, so it ends up becoming this here. The most important fact that you need to know is diamond is bonded to 4 other carbons. So no delocalized electrons, which, whoa, okay, that's fine. So it bonded to 4 other carbons. So no delocalized electrons. We'll come back to why that's important. Let's have a look at others first so we can compare. Now with graphite, this time carbon is bonded to 3 other carbons. So that means there's 1 delocalized electron. So you can already see how that's going to arise different properties of graphite. Now, graphite is what you find in pencils. So the lead that's inside pencils, that's made up of graphite. So this delocalized electron being free, it gives rise to hexagonal rings. So I'll just show you the graphite structure, how it changes completely. There you go. And there you go, the weak forces between the layers are also there as well. Okay, so there's your graphite. So I'll just put it here. Bonded to 3 other carbons, meaning 1 delocalized. I'm just going to write 1 free electron. Now, what that free electron gives to it, I'll come back to graphene, is graphite can conduct electricity because of this. That's the reason why, say, for example, they say don't allow children to stick things inside the sockets in the wall, especially pencils, because pencils conduct electricity because it's made up of graphite. However, diamond, because it has no delocalized electrons, it cannot conduct electricity. So electricity. So that's the reason why, if you think of the uses of diamond, what do we use diamond for? We use it for jewelry. That's the reason why it's good for jewelry. It doesn't conduct electricity. You're not going to be wanting your rings to be giving you electric shock each time. So that's what makes it good for its use. Another thing as well, because it's bonded to 4 other carbons, it is quite a strong structure, but they don't want you to use the word strong, as I mentioned yesterday in the biology class. They want you to use the word hard. So diamond is a very hard substance because each of them carbons are bonded to 4 other carbons. What else could I say about about diamond? Another use as well, so diamonds are not just used in jewelry. It's on some expensive drills, they put diamond on the end of it because of how hard the substance is. It allows the drill to be able to drill through quite difficult substances as well. Okay, and the reason why pencils can write with graphite is you can see these hexagonal structures, they roll over each other. So when you're gliding the pencil, that's what allows the writing to happen. Okay, so both made up of the same thing, carbon, but very different properties. The value of diamond compared to graphite is completely different because of how it's bonded. Okay, graphene. What's graphene? Well, graphene is just 1 layer. So you can see that top layer there. It's just 1 layer of graphite. Now, it's still a very strong material. Graphene tends to be used like in phones because it conducts electricity and it's very small. As you can see, it's just 1 layer. You can use it for quite a lot of things like that because it can conduct electricity, but it's also very strong and it's just made up of carbon as well. So if let's see. That's what it looks like. As we just said, just the 1 layer that's on top. Now, there's a few others that you can know about as well. So they're here actually, quite good. Um, Fullerene here. So fullerene is 60 carbon atoms altogether. That's in a spherical shape. And the uses of that is we can use it for drug delivery. So if you want to give medication to a person, you can put that medication inside a fullerene and then the person can take it in. And the reason why that's not dangerous is it's just made up of carbon. Carbon is an organic substance anyway. So let's put this on the page as well so you can see a few examples. Okay, so even though these are covalently bonded, you can see how their structure is very different compared to the simple molecules like carbon dioxide, water, hydrogen, and so on. So yeah, these are the giant covalent structures. Now, I'm just going to speak a little bit about another example of metallic bonding, and then I'll just give you a little break there as well. There is one other thing I forgot to mention as well. Polymers are also polymers, which are plastics, are also covalently bonded, so non-metals, but we're going to talk a little bit about that after as well. So with metallic bonding as well, so metallic bonding, you can either have pure metals or you can have alloys. So what's the difference? Now, pure metals is just one type of metal. So one type of metal, whereas alloys is a mixture of metals. The one we more commonly see that we use in everyday life is alloys, and you'll see the reason why. Now with pure metals, if you've just got one metal substance, just one type, so one size, this is what their structure is going to look like. All one size, and they can slide over each other. So let's take the example of like aluminium foil. So aluminium. Aluminium's quite soft. We use it to wrap food in to keep warm, and it's quite malleable. So malleable means it's bendy. And the reason why it's bendy is because it's just one size shape of metal that can slide over each other. Therefore, we're able to mold it and fold it. That's not ideal to use aluminium, say, for example, to build a door. You need an alloy for that. Now, alloy is a mixture of metals of different sizes. So let's say this is a structure. Now, as you can see, that's a mixture. It's not going to, the layers are not going to slide over each other. Whereas these will slide, which is what makes it malleable. So the alloys essentially are harder, therefore more useful than just pure metals. So pure metals, way too soft. Usually with the group 1 metals, when they're reacting with water, you see that they cut them. They can cut the metals, they're quite soft. So yeah, the more different size, two or more different sized atoms in order for it to not slide over each other. So I'll give you a 5 minutes break. We'll come back at 2 o'clock and then we'll continue from there. Okay, let's continue. So this leads nicely to starting to form equations and knowing what your product's going to be for the equations, understanding that we need to balance equations and why we need to balance them. So there's a law that you need to know about called the conservation of mass. Now, from physics, you should have heard of conservation of energy, which we'll speak about in tomorrow's session. But conservation of mass essentially means you cannot create or destroy mass. You're essentially changing it to something. So whatever's on your reactant side has to be on your product side. And that's the reason why we balance. So let's say, for example, do let's do a reaction of group 1 metal, so like sodium, but we'll use lithium instead. So it's also in group 1 as well. So if I show you the periodic table. Copy this down. So we can see lithium's in group 1, so the alkali metal. So these all react more or less the same way because they've all got 1 outer electron. Now, if I've got lithium and I react that with oxygen, now remember oxygen has to be diatomic. You can't just react it with O. That's how do I know what that forms? Now, a lot of people would just put LiO2. That's completely wrong. That's not how it forms. So what you do is, now you only do this with ionically bonded substances. So lithium is in group 1. So therefore, it has a 1 plus charge because everything in group 1 loses 1 electron. I'm going to put this here just to show you. Lithium has a 1 plus charge. Oxygen is in group 6. So it needs to gain 2 electrons. So everything in group 6 has a 2 minus charge. So you could do this along here. Everything in group 2 is a 2 plus charge because it needs to gain 2 electrons and it's metals. Everything in group 7 is a 1 minus charge. And remember, this is just with ionically bonded substances because they involve ions. So you could put that as well in the periodic table when you get into the exam as well. Okay, so oxygen is 2 minus. Now what you do is you put them down, and this is just the crossing method. So I don't know if anyone has seen this, but what you do is we don't care about the charges, but we're just crossing the numbers down. So the 2 comes down to the lithium, and the 1 comes down to the oxygen. Now, it doesn't make sense to write Li2 or 1. We don't need that 1, so we just write Li2O. So that's what the reaction becomes. So lithium 2O. So that's how we do it with ionically bonded substances. We cross them over. That's not balanced because we've got, if I list what we've got on each side, so we've got lithium and oxygen. Let me move this somewhere. And lithium and oxygen. We've got, on the left-hand side, we've got 1 lithium atom, we've got 2 oxygens, and on the right-hand side, we've got 2 lithiums, and we've got 1 oxygen. Now, this one's quite a straightforward one to balance. They won't give you a straightforward one in the exam. I would always recommend balancing questions, kind of leave to the end because sometimes it's kind of trial and error, and then come back to it because you only worth like 1 true marks. But yeah, list everything that you've got. Anything that's by itself, deal with it last. So both of them are by themselves in this case, so it doesn't really matter. Oxygen, I've got 2 on the left-hand side, so I need 2 on the right-hand side. So if I put a 2 in front of there, because we only can put numbers in front, the oxygen has become 2, so that's happy. But the lithium has become 4, because 2 times 2 is 4. So now let's balance the lithiums. There's 4 on the right-hand side, but there's only 1 on the left-hand side, so I need to stick a 4 in front of there. Now they're all balanced and happy. Now you can have multiples of balanced equations, meaning if I halved everything in that equation, remember there's an imaginary 1 in front of there. Half of 4 is 2, so 2 lithiums plus half of 1, which is a half oxygen, and then half of 2 is just 1, which we don't need to write, so lithium, oxygen. So you can have multiples. Some people don't really like putting halves in, so you could choose any of them, but as long as they balance, whatever's on the left-hand side has to be on the right. Let's have a look at another reaction. So you need to know group 1 reactions with oxygen. So they form metal oxides. So we call this lithium oxide. So group 1 metal plus oxygen gives you metal oxide. And you figure out the numbers by crossing the charges. Let's do one with chlorine. So if I had sodium and I reacted with chlorine, so Cl2, we get sodium chloride. So we're not going to get NaCl2. Don't just put that in the exam. Cross the charges and see what happens. So sodium is in group 1, which you can see here. Sodium's in group 1, so it's got 1 plus. Chlorine's in group 7, so 1 minus. So we just need to cross the 1s down, so NaCl. The 1 comes here, and the 1 comes here. I don't really need to write Na1Cl1, so I just write NaCl. And that's my answer. So sodium chloride. That's not balanced though. We've got 2 chlorines on the left-hand side, but we've only got 1 on the right-hand side. So if I put a 2 there, I've got 2 chlorines now, but now I've got 2 sodiums on the right-hand side. So I need to stick a 2 here. So the more you practice these balancing equations, the better you'll get at them really, and be able to just spot them without having to list everything down like I did here originally. Okay, so that's balanced. Equations must always be balanced no matter what. Even when anyone that is doing higher as well, when you start moving on to amount of substance, moles and stuff like that, you have to balance the equations in order for them to work. Okay, reactions with water as well. So what happens when I react sodium with water? So H2O. Well, what we get is we get a metal hydroxide. Now, what a hydroxide is, should know what this word means. A hydroxide is essentially OH minus ion. So we get a metal hydroxide, so sodium plus 1 plus, which we know it's in group 1. Then OH minus, so like 1 minus. If we cross them, we just get sodium hydroxide. The 1s just cross down. We don't really need to write them 1s. So we get sodium hydroxide, but we also get hydrogen. Now these become a bit more tricky to balance because you've got hydrogens in multiple places. So I'd recommend listing them all down here just because of the time of this class. I'm just going to balance this one for you. So you stick a 2 there, put a 2 here and put a 2 here, but you'd have to list everything down in order to be able to balance that. So remember, when you're reacting metal and water, you get a metal hydroxide and you get hydrogen. And remember, this hydrogen is flammable. You might have seen this reaction happen in school. When they cut a group 1 metal, so a really small piece, and they put it in water, it starts fizzing around. That fizzing around is the hydrogen that's essentially coming off it, which is flammable. They will only ever in school do it with these top ones. They won't ever do it with francium because that's very explosive. They might have shown you a video on YouTube of francium being thrown like in a bathtub, for example, at a distance, and it's very explosive because of that hydrogen. Okay. We need to know about displacement reactions. Let's go over displacement reactions. Now, what the word displacement means is displacing something out of place. So something that's more reactive will displace something that's less reactive. So you need to know about the reactivity series, and this is something that you do need to remember. So rather than me writing it down, let me find it somewhere. So reactivity. Yes, as you can see here. So this is something that you won't be given in the exam. You have to remember this. And it's for displacement reactions and to figure out when we're extracting metals, for example, if we can do a reduction with carbon or if we have to use electrolysis and so on. So it's really important. So as you can see, potassium here is a lot more reactive than zinc, for example. So anything containing zinc, the potassium will displace it out. Now the same goes for halogens. As you're going down, so Let me get an example actually. Okay, let's do this example. Let's say if we've got zinc and react it with copper sulfate. So we also need to know the sulfate ion as well. You need to know, so OH minus was an ion that you needed to know about. You need to know about the sulfate ion, which is SO4, and it has a 2- charge, something you need to memorize as well. So copper sulfate. Now what's going to happen here? Now if we look at the reactivity series, zinc is over here. Let me do it in red. So here's zinc, and copper is below. So zinc is more reactive than copper, so therefore we'll displace the copper. So what we get is we get zinc sulfate, and then the copper gets displaced, and that's already balanced. So that's essentially what a displacement reaction is. They won't ask you that straightforward in the exam, but if you do, you're quite lucky. What they'll usually say is, will this reaction take place? Like, will the zinc displace the copper? You'd say yes, because zinc is more reactive than copper, but it might be a trick question. You might get something like copper plus zinc sulfate. Will this reaction happen? Well, no, because the copper is less reactive than the zinc, so therefore no displacement will happen here. So displacement reactions are all about reactivity, how reactive something is. Let's talk about neutralization reactions as well. So neutralization reactions. Now, a neutralization reaction is to do with acids and bases. We spoke a little bit about pH yesterday in the biology class as well. An acid is something with a low pH, and base is something with a high pH. And if we react them together, what we get is a salt plus water. That's a reaction we get. Now, how do we know what's an acid and how do we know what's a base? Well, an acid is something that will have a H plus ion inside it. Now, hydrogen is the only exception whereby it's a positive ion. So remember how we said above that non-metals are negative ions? Where is it? So we said non-metals are negative ions. Hydrogen is the only exception to that. And you can remember that because on the periodic table, hydrogen is just free floating in the middle doing its own thing. So that's the exception. Now, anything with that H plus ion inside it is an acid. So to give you some examples, stuff like hydrochloric acid, you've got nitric acid, HNO3, you've got sulfuric acid, H2SO4, and so on. So they're the few that you do need to know about. Now, what's a base? A base is something that will have an OH minus ion, so the hydroxide ion. So a really common example of that is sodium hydroxide is a base. So that's how you recognize what's a base and what's a salt. Now, how do we know what's the salt that's formed? Now, what I'd recommend is when you're reacting your acid and base together, first just put your water out and whatever's left over is your salt. So I'll show you what I mean. Let's say, for example, we've got a hydrochloric acid and we react that with sodium hydroxide. Well, what's the salt that's going to form? I would say put your water in first, so H2O, and where your water comes from is the hydrogen from the acid and the OH from the base. So anything that's left over, in this case is sodium chloride, is what your salt is. So sodium chloride is a salt here. Let's double check the charges. Sodium's in group 1, so 1 plus. Chlorine is in group 7, so 1 minus. So crossing them over, the ones cross with each other, so we just get NaCl. And that is all balanced. That's perfect. So that's how we figure out what's the salt form. So we can pull out the ionic equation here. Now, what an ionic equation is, just the charges. The ionic equation of a neutralization reaction, as we just said, the H comes from the acid, so the H plus. And the OH minus comes from the base. And together, they neutralize each other because positive and minus, it's a neutralization reaction. We get water. That's fully balanced. We've got hydrogen, 2 on the left, 2 on the right. We've got oxygen, one on the left and one on the right, and the charges cancel. We've got a plus and a minus, which becomes 0, and we've got 0 on the right-hand side. So with ionic equations, you also have to balance the charges as well. So that's an ionic equation. Okay, so that's just in a nutshell neutralization reactions. Now, just for the last 15 minutes, I want to cover hydrocarbons. So what's a hydrocarbon? A hydrocarbon is a molecule that contains hydrogen, it's kind of in the name, and carbon only. So it just has them. And there's two types of hydrocarbons that you need to know for GCSE. We've got alkanes and we've got alkenes. So just differencing in the end word. Now, where do all these alkanes and alkenes come from? They come from crude oil. Now, what crude oil is, think of fossils, essentially. Crude oil is oil that's been extracted from under the ground. It's taken millions and millions of years to form. It's a finite resource. So once we finished it, we finished it. We have to wait another millions of years for it to form again. And it's extracted from underneath the seabed, created over millions of years. It's dead animal and plant matter from that time as well. And from that crude oil, because it's a mixture of hydrocarbons, we have to separate it into these alkanes and alkenes, and that happens with fractional distillation. Fractional distillation, which we'll go over. Okay, so what's some of the things that are contained within this crude oil? Well, alkanes and alkenes. You need to be able to name them, draw them, and know what they are. So alkanes are the ones where between the carbons, you've got single bonds. And alkenes are the ones where you've got double bonds between the carbons. And the way we name them, well, there's a mnemonic that I've remembered. I'm just going to put it up here. You don't have to use this mnemonic. You could come up with your own. But I've used this since GCSE and it's still there. So monkeys eat peanut butter. So we've got MEPB. Okay, so the M starts for meth. The E stands for eth. The P stands for prop. And the B stands for bute. So that's essentially the word that comes before it, so the prefix between. So alkanes all end in "ane." So the first one is methane. Got the H. So methane has just one carbon. So one carbon, and remember we said carbon can bond to 4 other things. Remember with diamond because in group 4. So this just bonds to 4 other hydrogens, and that's it. That's methane. The next one is ethane. Okay, can you hear me now? Okay, sorry about that. I've got no idea what's going on there. Okay, so ethane, 2 carbons, and then you've got your hydrogens there as well. Next, if we look at the mnemonic, so monkeys eat peanut, so prop. So propane, 3 carbons this time. 1, 2, 3. This carbon here on the left has already 1 bond, so it needs 3 more. This one in the middle already has 2 bonds, so it needs 2 more. And this one here finally has 1 bond, it needs 3 more. So if you end up having 5 sticks outside of your carbon, you've definitely gone wrong. Each one should have 4. Okay, that's propane. And then finally butane, which is 1, 2, 3, 4, is like so. That's butane. Sometimes they don't put in all these hydrogens, they just leave it as sticks just because it's annoying to draw them. Now remember, these carbon chains can get very long. You can even get a carbon chain like with 20. carbons on, but they do expect you to know the first four for each of these. And the ones after, so the ones with 5 carbons, what's a 5-sided shape? Pentagon. So pentane is a 5 with 5 carbons. We've got pentane. Hexagon is 6-sided shape, so hexane is next. Heptagon is a 7-sided shape, so heptane. So it just follows the mathematical shaping um, wording. Octagon has 8 sides, so octane has 8 carbons in its alkane. We've got nonane and decane. So it just follows the shape order after that. I'd say the first 4 don't really have a pattern. Okay, let's count how many carbons and hydrogens each of these have. So carbons, there's 1 here. I don't really need to write that 1. And I've got 4 hydrogens. So methane is CH4. Ethane, we've got 2 carbons. And we've got 1, 2, 3, 4, 5, 6 hydrogens. Propane, we've got 3. We've got 8, 2, 4, 6, 8. Finally, for butane, we've got 10. 2, 4, 6, 8, 10. Okay, so there's a way you can remember that without having to draw them. And the formula for that, I'll put it in red, is CN H2N plus 2. So whatever you make N, so for example, if I make N1, let's use it down here. If I make N1, so for methane, C1 H 2 times 1, so 2N, 2 times 1 is 2. So we've got 2 add 2, so C1 I don't need to write. H2 add 2 is 4, so CH4. So you can see it works. So remember this generic formula for alkanes as well, just in case, I don't know, you have to do it for something with 20 carbons, then you can do let N equal 20. So C20, H, 2 times 20, which is 40. 40 add 2, 42. That's how you just figure out how much hydrogens and carbons is in a certain alkane. You need to know the uses of these as well. So the short chain ones tend to be used for petrol, or like when you're going camping and you put that like kind of substance inside the tranche and then you light it, or even with bonfires and such. These are all the short chain hydrocarbons that we've just spoken about. Okay, what about alkenes? Let's go over alkenes now. So alkenes, now methane doesn't exist, and you'll see why. Let's move over to ethene. Keep a line here. Ethene. So remember, eth means 2 carbons. 1, 2. And remember, we said with alkenes, it's a double bond. So I'm going to stick a double bond here. So if I just had, like, think with methane, if I had a single carbon, where exactly do I draw the double bond? That's why methane doesn't exist. Now, remember, each carbon needs 4 bonds. This carbon here already has 2 bonds, so it needs 2 more. And this carbon here already has 2 bonds, so it needs 2 more. So that's what ethene looks like. Let's count the number of carbons. So we've got C2H, 1, 2, 3, 4. So you can see how it's different to ethane. Let's do propene. Now this is where people make the mistake. Propene will have 3 carbons and double bond between the carbons, but you do not put the double bond everywhere. You just choose one place to put it and you keep it there. So you can choose there, or you can choose on the right hand side, but do not stick more than one double bond in. Now let's fill in our hydrogens. This carbon here has 2 bonds, so it needs 2 more. 1, 2. This carbon in the middle has 3 bonds. 1, 2, 3, so it needs 1 more. And finally, this one at the end has 1 bond, so it needs 3 more. So let's put in our hydrogens. So we can see there's 3 carbons, C3. How many hydrogens do we have? We've got 1, 2, 3, 4, 5, 6. So you should already notice the pattern that's happening here. Let me move all these a bit further up so I can fit butene in. write that again. Okay, let's do butene. So butene has 4 carbons. 1, 2, 3, 4. It needs a double bond. Just choose anywhere to put that one double bond. I'll just choose in the middle. And let's put hydrogens in. This one needs 3. This needs 1. This needs only 1. And this needs 3. Sometimes you might see the diagram just left like that. So I'm just going to leave it like that just so you get used to that. And this is C4H8. So you should notice a pattern here. With alkanes, it was this. So with alkenes, it's CnH2n, and that's it. That's what the formula is for that one. So what's the uses of alkenes? Alkenes are used for polymers. Now, polymers are just the scientific name for just plastic, essentially. So anything that's plastic is a polymer. So this is made up of ethene, essentially. Or polypropylene, or you should, when you look at certain bottles or anything that's plastic, there might be a triangle symbol on it somewhere. And that tells you what kind of plastic it is as well. So whether it's recyclable and such as well. So they all come from alkenes. So we've got 5 minutes left. So I'm just going to talk a little bit about combustion. And just keep it here. And then we'll wrap it up there. So what is combustion? Combustion is essentially a way of making energy using fuels. So a bit like respiration, but for the cars, essentially. Combustion is what cars action. So what happens is you have a fuel, and that fuel is going to react with oxygen in the air, essentially. So you put fuel into the car, in the engine, that's going to react with the oxygen, and what happens is carbon dioxide is formed as well as water. So yeah, that really is, it is like respiration in a sense, but with fuel. So let's do an example. Now, all this chemistry that we've just spoken about at the end, we call this organic chemistry. The reason why we call it organic is because it's got stuff like carbon, oxygen in, and stuff. These are all organic atoms. So this is complete combustion. Remember how we said with respiration, there's aerobic and anaerobic respiration. And aerobic respiration happens with enough oxygen, and anaerobic respiration happens with not enough oxygen. Well, complete combustion happens when there's a lot of oxygen, so there's enough oxygen. Whereas with incomplete combustion, so incomplete combustion, this happens when there's not enough oxygen, so the fuel's not burning fully. So what happens is that fuel will react with the oxygen, but there's not enough oxygen. So instead of carbon dioxide being formed, carbon monoxide is formed. So mono means one, and water. So the issue with carbon monoxide is you can't smell it, so it's got no smell, you can't see it, but it can kill and cause respiratory problems. So that's the reason why legally you have to have carbon monoxide alarms in your house, just so you know if there's carbon monoxide present in the room, because you wouldn't be able to smell it or see it. So that's much more dangerous than carbon dioxide. Now there's issues still with carbon dioxide. It's a greenhouse gas, so causes global warming. That's the reason why they're trying to push away from these petrol and diesel cars and move towards electric cars to stop this process from happening. So just want to give you a quick example of complete combustion. Let's say we've got ethane, which is C2H6, which you've seen up here. That's the fuel. It reacts with oxygen, that forms carbon dioxide plus water. So just balancing that, I can see there's 2 carbons on the left-hand side. So put a 2 there on the right-hand side. We've got 6 hydrogens on the left-hand side, and I've only got 2 here, so I'm going to put a 3 in front of there. 3 times 2 is 6. Now let's look at oxygens. We've got 2 oxygens on the left-hand side. On the right-hand side, we've got 4 here, so 2 times 2 is 4. And we've got 3 here because 3 times 1 is 3. So we've got 4 plus 3, which is 7. So how can I change this 2 to a 7? Well, I can times by 3.5. So just put 3.5 there in front. Now, this is a lot more skilled balancing, like me being able to do it in my head, but you can list everything out and work with it that way as well. Again, if you don't like dealing with that, half times the whole equation by 2. So I would get 2C2H6 plus 7O2 gives you 4CO2 plus 6H2O. So yeah, you get better at it the more you practice. So we'll wrap up the class there. I'll get the recording out and I'll get these notes sent out as well. And I hope you found that useful. And I will see you tomorrow for physics content class as well. But thank you for joining. Hope you found that useful.